Okay, this is the lab for 4.1, and you can do this either of two ways. You can do what I'm doing and print everything off and get it like this, or you can actually do the end product on Notability. It is up to you how you do this. You can make it as neat as you want and colorful as you want. It's supposed to be a fun activity during our class time. But the more important part is for you to become more familiar with the atomic structure and these subatomic particles. So what I've already done is there's an attachment on PowerSchool for this section with the lecture 4.1 as well, and it asks you to download a document, and this is going to be the protons, the neutrons, and the electrons, and you can either do that again or you can do this on Notability. I've already cut them advanced, and I'm going to go ahead and begin. What we're going to be doing is we're going to be taking a look at one of the atoms, and the atoms we're going to be taking a look at is going to be fluorine. Fluorine is an element that you find in toothpaste. It's commonly known as fluoride. But fluorine, the symbol is a capital letter F. And I want to give you some pieces of information about fluorine. I'm looking up the periodic table in my room right now, and if you look at the box that it's located in, it has that capital F. So this is something that I want you to all record on your sheets. And it has a number 9, which we talked about the significance in the lecture notes, and underneath it is an 18.998. Let me get that volume off. So 18.998, okay? So first of all, we should probably list over here the particles that we have. We have the P, we have the N, and we have the E. You're welcome to color these in if you want. I am simply going to be using the black and white that I currently have. You can tape them or you can glue them. It doesn't really matter because you're going to be taking a picture of this and sending it in anyway. So here are my 3 subatomic particles. So let's go ahead and list their names again. So P, if you remember, is our, N is our, and E is our what? You can refer to your lecture notes for this. And feel free to pause this at any time, and you can guess the name of it. I'm going to continue to go on. P is the protons. N stands for the neutron. And E stands for the electron. So the question is, how many do I have of each of these in my atom? And we can find that information right here. So to remind you from our lecture notes, this 9 is very, very significant, this number on the top. This tells us 3 things. This is called the atomic number, but it also tells us the number of protons, and it also tells us the number of electrons. So it tells us those 3 things. It's the atomic number, it tells us the number of protons, and it tells us the number of electrons. So going over here, how many protons am I going to have? It's the atomic number right here. So I'm going to have 9 protons. Atomic number is also equal to the number of the electrons. But it does not tell us the number of neutrons. That is something we need to calculate. Now, if you remember, the protons and the neutrons, these are found inside the nucleus. And it's this that gives us the mass of the atom. The subatomic particles of the protons and the neutrons give the atom its mass, and those are found on the inside, and that is called the nucleus. So we have the protons plus the neutrons equals this number. We can actually round this number. This number is going to be called the mass number. And when you round the 18.998, the mass number for this is going to be 19. Well, if I have 9 protons of my 19, how many neutrons will I have that will add to 19? We can do a calculation from your lecture notes. The number of neutrons is equal to the mass minus the number of protons. Another way of saying that is the protons plus the neutrons will equal the mass. But here's the formula. So take the mass. My mass is 19. My protons is 9. Therefore, my number of neutrons is going to be 10. It's going to be 10. So what I'm going to do is I'm going to be removing my subatomic particles out of the way so we can start to build this. And again, what you can see is we can see these rings, and these rings are called the shells for the electrons, or they're called the electron shells. The inside portion right here, this is where my nucleus is going to be. So I'm going to count 9 protons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I'm going to be counting 10 neutrons. I'm going to count them over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 neutrons. That's going to all go in the middle here. So it does not matter how these are arranged. I'm just going to put them like this. I just want to make sure all these protons are going to be visible, and it's going to be looking something like that. Okay? Now, your neutrons are going to be kind of stuck in between. It doesn't matter how these are positioned. In physics, we learn a little bit more about the forces that are on the inside of the nucleus. These forces are called these strong nuclear forces, and it's what holds all these protons and these neutrons stuck together in this cluster. Because if you think about the charge of a proton, charge of protons is positive. And you have these other things that are neutrons that are neutral. The charge of those guys is 0. Well, what holds these things together? There's really nothing to attract a positive and something that's neutral. And these are our strong nuclear forces. So I am just simply going to put them together like this. And again, you're welcome to glue them. I'm just putting them all together like that, and I think they're all stuck right there. So we talked about in lecture how the electrons are not just swarming like a bunch of bees around a beehive. They're actually in very particular orbits. Think of this being like the Earth, and this being like the satellites that go around the Earth, or this being the sun, and this being the planets. There's very particular orbits that the planets follow, that the satellites follow. And it's very, very true for our electrons as well. And our electrons occur in very specific numbers. The magic number for the electron shells, here are our shells. We have 3 shells. Here's our first, here's our second, and here's our third. So we have the shells of 1, 2, and 3. And the magic numbers that are going to fill those are going to be 2, 8, and 8. That's going to be taken from lecture. So if you can take your electrons, and we're going to put 2 electrons, does not matter where, in this first inner shell, and it's going to look something like that. Well, how many more electrons do I have? I actually have 2 in the first. I have 9 total. So how many are going to fit in this next shell? I'm going to have 1, 2, 3, 4, 5, 6, and then I'll have 7. my 2 in my first shell, plus the 7 that I have. I actually don't have 8 because if I had 2 and 8, I'd have 10 electrons, but this atom only has 9 electrons. So my 2 on the inner shell plus the 7 on the second shell, that makes my 9 electrons. Now, if I had the next element, which is neon, neon actually is element number 10, and therefore it would have 2 electrons in the first shell, then it would have 8 in the second shell. The next element on the periodic table is sodium, which is 11. How would you fit 11 electrons within the first 3 shells? 2 in the first, 8 in the second. How many would fit? We can fit up to 8, but we don't have 8 more. It's element number 11. It's 2 plus 8, which makes 10. 1 more would make 11, and we'd have a lone electron going in this third shell right here. That's it for this lab.